Every time you generate an SSH key, create a TLS certificate, or encrypt a file, something strange has to happen. Your computer, a machine that does nothing but execute deterministic instructions, needs to produce a number that nobody, not even itself, could have predicted. If an attacker can guess that number, your encryption is worthless. The entire security of the internet rests on a problem that shouldn't even be solvable on a deterministic machine. So, how does a computer produce something truly unpredictable? Today, we are going to answer that question. Let's start with why this matters. Cryptography depends on randomness. When you generate an RSA key pair, you pick two massive prime numbers at random. When you start a TLS handshake, you generate a random session key. When your password manager creates a new password, it pulls random bytes. If any of these numbers can be predicted, the cryptography built on top of them collapses instantly. And this isn't theoretical. In 2008, a maintainer patching Debian's OpenSSL package accidentally removed the code that mixed unpredictable data into the random number generator. For 2 years, every Debian system generated SSH and SSL keys with only about 32,000 possible values. Attackers could brute force any key generated during that window in seconds. Every affected key on the internet had to be revoked and regenerated. In 2010, a group called Failoverflow broke the security of the PlayStation 3 because Sony's code reused the same random number for every cryptographic signature. Once that was discovered, the entire console's chain of trust fell apart. When your randomness fails, everything fails. So the question becomes, where does this randomness come from? Let's start with what computers can do on their own. Every modern operating system ships with a pseudo-random number generator, a PRNG. It's just an algorithm. You feed it a starting value called a seed, and it produces a long, statistically uniform sequence of bits. Run it again with the same seed, and you get the exact same sequence. That's why it's called pseudo-random. It looks random, but it's completely deterministic. PRNGs are great for simulations, games, or any situation where you just need numbers that spread evenly. But for cryptography, they have a fatal weakness. If an attacker can figure out the seed, they can regenerate your entire sequence. And a 32-bit seed has only about 4 billion possible values, which sounds like a lot until you realize a modern GPU can try billions of values per second. So we don't just need pseudo-randomness, we need the seed itself to be unpredictable. And to get that, we have to step outside the deterministic world of the CPU and sample something from the physical world. That's where entropy comes in. In information theory, entropy is a measure of unpredictability. A coin flip has one bit of entropy because there are two equally likely outcomes. A roll of a fair six-sided die has roughly 2.58 bits. The more uncertain you are about an outcome, the more entropy it carries. In the context of operating systems and cryptography, entropy means something more concrete. It refers to data collected from sources that are genuinely hard to predict, even if the attacker knows everything about the machine's software and hardware. The problem is, your CPU executing instructions is not such a source. Given the same inputs, it will always produce the same outputs. That's literally its job. In that case, you have to look elsewhere. You have to look at the physical world. And this is where your mouse becomes a cryptographic instrument. When you move your mouse, the operating system receives a stream of events. Each event contains a position, and each event arrives at a specific point in time. Now, the position itself has some unpredictability, but the real gold is in the timing. The kernel measures the interval between mouse events down to the nanosecond. Those lowest few bits, the microsecond scale jitter between one interrupt and the next, are determined by a cascade of tiny physical effects. The exact way your hand trembles, air currents, thermal variation in the mouse sensor, the precise moment the USB controller decides to deliver the packet. Nobody, not even you, controls these bits. The kernel takes those low-order bits and feeds them into something called the entropy pool. And mouse movements are just one source. The kernel gathers bits from everywhere it can. Keyboard input, not what keys you press, but the exact timing between keystrokes. Disk I/O, how long it took the hard drive head to seek to a given sector. Network interrupts, the arrival time of incoming packets. And on modern hardware, dedicated CPU instructions like RD-rand and RD-acid on Intel chips, which sample thermal noise from a tiny on-chip circuit specifically designed to be unpredictable. Each of these sources produces bits that are only weakly random on their own. A mouse interrupt might yield only 3 or 4 truly unpredictable bits, but if you mix enough of them together, you accumulate real entropy. Now, how does the kernel actually mix them? The entropy pool is a fixed size buffer of bits. When new data arrives from a source, the kernel doesn't just append it, it runs the input through a cryptographic hash function together with the existing pool content and writes a result back. This is called the mixing function. Its job is to ensure that even if an attacker knows some of the inputs, they can't deduce the pool's current state. On Linux, this whole machinery is exposed through two special files, dev-random and dev-urandom. When a program needs cryptographic randomness, it reads from one of these. Behind the scenes, the kernel pulls bytes from the entropy pool, runs them through a cryptographically secure pseudo-random number generator, currently based on the SHA-20 stream cipher, and hands the output to the program. You might be wondering why there are two files. Historically, dev-random blocked. If the kernel thought the entropy pool didn't contain enough fresh bits, a read from dev-random would just pause until more entropy was gathered. Dev-urandom, on the other hand, never blocked. It would keep producing output from the internal CSPRNG indefinitely, even if no new entropy had come in. For years, this distinction caused massive confusion. People assumed dev-random was more secure because it blocked, so they used it for key generation, and their programs would hang for minutes on headless servers with no mouse and no keyboard. Modern Linux has mostly unified these. Once the pool has been seeded with enough entropy at boot, usually a few hundred bits, the CSPRNG output is cryptographically indistinguishable from true randomness. At that point, dev-urandom is exactly what you want for almost everything. This brings us to one of the most fascinating failure modes in computing, the freshly booted virtual machine problem. When a VM first comes up, it has no history, no mouse movements, no keystrokes, no real disk seeks. The disk is virtual. The entropy pool is nearly empty. If the VM tries to generate cryptographic keys in the first few seconds of its life, those keys can be weak because the CSPRNG was seeded from only a tiny amount of entropy. In 2012, a group of researchers scanned the entire public IPv4 internet and collected every TLS and SSH key they could find. They discovered that tens of thousands of servers were using RSA keys that could be factored, and an even larger number shared keys with other servers. The common thread was that many of these keys had been generated on freshly provisioned VMs or embedded devices that simply didn't have enough entropy when they booted. Two machines, starting from nearly identical empty pools, had produced nearly identical random primes. This is exactly why you'll see tools like GPG tell you to move your mouse and press random keys while it generates a key. It's not a gimmick. The program is explicitly asking you to pump entropy into the pool because it doesn't trust what's already in there. Your physical movements are being converted bit by bit into cryptographic seed material. Modern systems have layered defenses against entropy starvation. The Linux kernel now supports something called jitter entropy, which exploits tiny, unpredictable variations in how long simple CPU operations take, caused by cache effects, memory timing, and other microarchitectural details. Hardware RNGs on modern CPUs provide a constant stream of entropy. Virtualization platforms now pass entropy from the host into the guest through a virtual device called virtio-rng. All of this means the my VM has no entropy problem is much less common than it was 10 years ago, but the underlying principle hasn't changed. Step back and look at what's actually happening here. We have a deterministic machine. Every instruction it executes is perfectly predictable given its inputs. And yet, through a chain of tiny couplings to the physical world, a mouse nudge, a thermal fluctuation, a packet arriving a few nanoseconds late, it manages to produce numbers that no adversary can predict. The deterministic world reaches out, grabs a handful of chaos from reality, hashes it, stirs it into a pool, and uses it to derive the keys that secure every encrypted connection on the internet. Every SSH key you've ever generated, every HTTPS session your browser has negotiated, every encrypted message you've sent, somewhere in the lineage of the random numbers behind it, there is a bit that came from a tremor in somebody's hand, the jitter of a hard drive head, or the thermal noise of a few transistors. Cryptography doesn't work without that link to the physical world. The whole system is built on the assumption that reality contains more unpredictability than any algorithm can fake. And that's entropy in computer science, not just an abstract measure from information theory, but a concrete resource, something the kernel actively farms from every physical event it can observe, so that when your program asks for a random number, it has something real to give.